Okay, this is the second intro then for chapter 1. And just a couple of things I want to kind of emphasize here before I kind of wrap up chapter 1. I alluded to one of these in the earlier video, which is about energy. So I want to kind of make a comment about that. I'm going to point you to a spot in your book. I hope it's the same as mine. But basically in mine, it's in chapter 1, and it's in the section called The Importance of Energy in the Study of Matter. And it's got some pictures that depict, again, I'll show them here just to see if you have the same pictures. There's 4 pictures in this section that refer to energy situations, and what they're trying to show is that there's several different ways of looking at high energy versus low energy situations. There's one picture that shows a weight that's hanging way up in the air. Okay, so it's hanging up in the air, and then it shows the second picture where the weight drops down to the ground. And what it's trying to say is that when the weight is up high, it's in a high energy state, and when it's low, it's in a low energy state. Essentially what it means then is that if you want to move from a low energy state to a high energy state, you need to exert energy. I mean, you need to lift this object. In this one case, you need to lift the object, and you'll have to actually exert work to move the object from a low energy state to a high energy state. Naturally speaking, if you just left it on its own, the weight would want to, if you think of it that way, go to a low energy state, meaning if it ever had the opportunity to fall, it would go crash down and reach this low energy state. In the process, of course, it would give off some energy. When it hit the ground, it might break something, or it'll make a sound, which is energy, or it might even cause a spark if it hit like a piece of metal. All of those things are cases where energy is being released by this change. Here it's basically a change of a weight going from a high spot to a low spot. There's another picture in here that talks about a spring, which is if you have a spring that's compressed, it wants to release. It wants to push out, that is another energy state where when it's compressed, it's at a high energy state, and when it's released, it's at a low energy state. In the same sort of way, in the other picture, is that if you had a low energy state, like the spring is relaxed, it requires energy to compress the string to reach the higher energy state. That's really similar. It's analogous to this case where we talked about with gravity. There's 2 other cases. I want to talk about them because they're kind of important. One talks about the third case talks about charged particles, particles that are far apart. One's positive, one's negative. When they're far apart, they're actually at a higher energy state, because naturally speaking, they want to attract each other. So the low energy state is when the positive particle and the negative particle are together. Think of like a magnet. If you have 2 poles of a magnet, they want to stick together. It takes energy. Basically, you have to pull them apart to reach a state where they are separated. So in this case, it's showing positive, and they mean electrically charged positives. But again, like I said earlier in the earlier video, electricity and magnetism are really just kind of mirror images of each other. So you can think of it in terms of magnets that you're pulling apart. The last picture is the most important one, because this is where it takes it into chemistry. The last picture talks about a high energy state of a compound like gasoline. Gasoline is a set of compounds that are at a high energy state. Naturally speaking, those high energy compounds want to break down into lower energy compounds. And so in the case of gasoline, the gasoline, which is high energy, wants to break down into water and carbon dioxide and other byproducts that would show up in your car exhaust when you run the engine. So what the combustion engine does is allows us to, in a controlled fashion, take the high energy compounds and have them reach a state of low energy compounds, and we very cleverly capture some of the energy that's released in that process. And that's what the combustion engine does. But the reason why I focus on this is that reaction, or that change of the high energy compounds, gasoline, to the low energy compounds, carbon dioxide and water, is a chemical reaction. So this shows that this concept of energy states, being high energy and low energy states, definitely applies to chemistry. In fact, chemistry doesn't work without it. Chemical reactions are all about deciding which is the high energy state, which is the low energy state, knowing that the compounds are going to naturally gravitate towards the low energy state. Again, we'll see that over and over again as we study chemical reactions. And a lot of times you'll see that in order to get a reaction to take place, you actually need to add energy. In the same way that we were in these other examples, if you want to move a weight from a low energy state to a high energy state, you need to add energy to create that. So that's why it's possible to actually have a chemical reaction that actually moves the reactants from a low energy state to a high energy state. That only works, however, if you add energy, like if you turn a flame on and you boil up the contents that you hope to react. So again, that was one I wanted to cover, and it's really kind of important to get those concepts, and we can talk about this as well, because again, energy is central, is almost as central to chemistry as electrons are, like I focused on the last time. The last piece that I want to cover in chapter 1 is it's towards the end, and it's a spot where, in my book, it's figure 110, 1.10, and it covers a number of relative sizes using both distances and masses and volumes of things. And you know, it's kind of like fun fact kind of stuff that, like, if you added up all of the liquids in the oceans, then it's 10 to the 24th liters, which sounds like a big number, but you know, whatever. But then if you go all the way down to the volume of a carbon atom, it's 10 to the minus 27 liters. So we have one really gigantic volume, which is the sum of all of the liquid on Earth, and then a really tiny one, which is the volume of a single carbon atom. Now what's interesting to look here is that sometimes if you look at these cleverly, the oceans are 10 to the 24th, and the carbon atom is 10 to the minus 27th. So it's almost like the positive and the negative of these numbers are quantities that we can at least grasp. We can conceptualize that a carbon atom is really, really tiny, and a vessel that held all of the liquid on Earth would be really, really giant. And numerically, here are the numbers: 10 to the 27th, or 10 to the 24th, and 10 to the minus 27th. Okay, so that's kind of good. If you look at the mass, then the mass is another interesting one. The mass, and it doesn't show this in your book, but the mass of planet Earth is 6 times 10 to the 27th grams. So obviously planet Earth is a massive object. This is one big object. Now, of course, it's not even the biggest object in our solar system, not even close, right? In fact, it's one of the smaller objects in our solar system. But yet, it's 10 to the 27th grams. On the other hand, the mass of a water molecule is 10 to the minus 23rd grams. So again, now one big object, one small object, and these numbers are 10 to the 27th, 10 to the minus 23rd. It's almost as big as it is small when you look at it. Now, the reason I mention this is that, and this is another kind of key takeaway from chapter 1, is that chemistry is all about macroscopic observations of matter that we make with our eyes and with our senses, that really truly take place at a microscopic level. So these chemical reactions, and throughout this book, we're always going to be talking about atoms as though we can actually imagine one atom of one compound reacting with another atom of another compound, because we're able to kind of draw models to see why that happens. But they're incredibly small. I mean, they're like, it's as small, it's as different as these differences we're looking at here, the size of all the oceans and the size of a carbon atom. So really, really small events actually dictate what happens at a macroscopic level. Now, the only reason I'm emphasizing this is that we're going to be dealing with these kind of gigantic scales all the time in chemistry. You always deal with the really, really, really tiny, but all of that ends up translating to macroscopic, really, really large events that we can observe. Okay, so that was just wanted to cover that, and just to kind of put it in perspective, this little shot glass, I should show you the plums, has, and I calculated it, 10 to the 23rd or 10 to the 24th water molecules. It's this tiny little bit, but it has a gigantic number of molecules. I mean, really just ridiculously large. And along the lines of these numbers that I've been using so far, it's almost like for every molecule we have in this glass, if you added it all up, it would be like taking a liter of ocean water, and for every liter, you have that many to fill the entire, to hold all the water on Earth. Maybe this is hard to translate, but anyway, get used to the number scales here, because that actually plays a big role as you do computations in chemistry. Okay, that's all I wanted to cover for chapter 1. Again, I think you've already done the examples in chapter 1 too, so I don't think there's any that I saw that are worth going through. We can talk about that as well. Next, I'm going to pick back up on chapter 2, and I'll probably do this in at least 3 chunks. I'll probably have a kind of an overall intro piece, kind of like I did in the first chapter, and then I'll cover the 2 main concepts of chapter 2. So that's coming up soon.